Let's apply implicit differentiation to some real life problems. They're called related rates, and that's because as you change one rate, another change will also occur with the other rate. So for this, we're looking at supply and demand in relation to price. So as price goes down, the demand is going to go up, right? When you see a really good sale, you are more likely to buy it, versus when price goes up, the demand goes down. We're willing to wait and see if there's going to be a better price. And then we're also looking at supply. So supply is on the other end. You're the one selling something. So if you raise your price is increasing, your supply is going to go up because things are going to sit on the shelves and not really sell very well. Versus if you have a huge sale, it's like Black Friday sale, your shelves are going to be emptied because your price goes down, your supply is going to go down because people are buying it. So we want to think about both perspectives. So for this first one, we have a manufacturer of disk drives is willing to make X thousand flash drives available in stores. So if we see X is 4, that doesn't mean they're only having 4 drives. It means 4,000 drives in stores each week when the wholesale price is P dollars per drive. So I might just pause and go off to the side here and write out these variables I'm given. I'm given X, which is in 1,000 drives, and P, which is the price per drive. So that's in dollars. And since we're going to be taking the derivative of this, we're going to take the derivative with respect to time and neither our time. So once we know that we're working with X and P, we're also going to get a dx dt as well as a dp dt. And when we do that, we're going to look at the time frame here. It's saying available in stores each week. The relationship between X and P is given by the supply equations, and we're looking at drives per week. So this dx dt is going to be in 1,000 drives still, but it's going to be per week. It's a rate of change. It's our derivative of X with respect to time. dp dt is going to be in dollars from P per week with time in the denominator there. So we can set up our variables and their respective derivatives with respect to time off to the side there. That's going to help us sub in some letters. And we have this equation that I'm going to copy down here. This is our supply equation. So we're talking about supply this time. We're thinking from the perspective of the business owner, and we're thinking about how much is going to be sitting on the shelves depending upon what we do with the price. As price goes up, we're going to have more supply. As price goes down, we're going to have less supply, typically. So our equation we are looking at is x squared minus 3xp plus p squared equals 5. That's what we're going to end up taking the derivative of. So we are not even done reading the problem, but we can tell our two variables are x and p either by looking at the first sentence or looking at the equation, and that's going to be what we're going to take the derivative of each time. So we want to figure out how fast is the supply of drives changing when the price per drive is $11. So which letter is that going to be? Price per drive. Well, it's definitely not going to be X or dx dt. We're talking about the price, so it's something in dollars. And does it say it's increasing by $11 per week or decreasing by $11 per week? No, it's not a rate of change. It's just a regular variable. The price per drive is currently $11. There's our current P. The quantity supplied is 4,000 drives, so be careful. This is going to be either X or dx dt, because we're talking about the drives, not the price. And it's not a rate of change. It's not saying it's decreasing by 4,000 drives per week. It's just in drives. And we want to make sure we put X as being 4. That stands for 4,000 drives. And the wholesale price per drive is increasing at a rate of 10 cents per drive each week. So we're starting to raise our price. We want to see, is our demand going to still hold strong or is it going to start to drop? So our price is increasing. Is that dx dt or dp dt then? It must be dp dt. And it's 10 cents per drive each week. And if I didn't take the time to do that setup with xp, dx dt, and dp dt with those units, I would probably plug in some of these numbers wrong. For instance, X is 4, that stands for 4,000. And then the other thing is 10 cents per drive each week. Well, price is supposed to be in dollars, so instead of plugging in 10, I'm going to plug in 0.10, or 0.1 stands for 10 cents per week. And we want to figure out, is that derivative supposed to be positive or negative? Are we increasing our price or decreasing our price? It says increasing, so dp/dt is going to be a positive $0.1 per week. We're raising our price. How is that going to affect our supply that we have sitting in stock? Are things still going to sell well because it's just a tiny price increase, or are we going to have a lot of things sitting on the shelves not being sold? So the related rates, you're always given how one thing is changing. So here we have the price is increasing, and we're solving for how the demand is affected, or the supply is affected for this one. You're always going to be given one rate and asked for the other. Always solving for a rate. So now I'm going to go ahead and take this derivative with respect to time. It's going to be a regular derivative, but every variable gets a d something dt. So for the first piece, we're taking the derivative of x squared. So I'm going to bring down the power, and my derivative is going to be 2x dx dt. The next part is a pain. I have minus 3x times p. So I actually have a product rule here when I take the derivative. So I'm going to call the first factor negative 3x and the second factor p. So I'm going to do derivative of the first. Derivative of negative 3x is going to be negative 3 dx dt. I like to put those at the end, so I'm going to move that over here. Derivative of the first factor is negative 3 dx dt times the original second factor is a p. Product is always plus. So we did the derivative of the first times the original second was p. Now we're going to do the derivative of the second. Derivative of 1p is just 1 dp dt. And we don't even necessarily have to write 1 because multiplying by 1 doesn't change anything. Really, the derivative of 1p is just 1 dp dt times the original first is a negative 3x. So it's up to you. If you want to put the 1 in, you definitely can. You also don't have to. Multiplying by 1 doesn't change anything. But we can double check our product rule. We have the derivative of the first is negative 3 dx dt times the original second is p. That looks good. Then we did the derivative of the second. We got 1. Derivative of 1p is just 1 dp dt times the original first is negative 3x. All right, next piece, derivative of p squared is just 2p dp dt. And then finally, don't forget to take the derivative of the other side as well. Derivative of 5 is 0. So we don't bring down the 5, we take the derivative of it. So now we have this big thing to plug into, but I know everything except for dx dt. So I'm going to sub in all of these numbers. I'm going to replace all the x's with 4's. So I'm going to start with 2 times my x value is 4. That stands for 4,000 drives. Then we have dx dt, the one thing we're trying to solve for. Then we have negative 3 times p. The current price is $11 times dx dt, again, what we're solving for. Then we have 1 times negative 3, which is really just going to be negative 3. When we combine those two numbers, 1 times negative 3 is going to be negative 3 times my x value is 4. That stands for 4,000 drives. And we also know dp dt is a positive 0.1. Increasing our price by 10 cents per week. And then we have plus 2 times our p is $11 times another dp dt, which is 0.1 equals 0. So lots of things to plug in, but I actually think this is easier to solve than implicit equations. We don't have to do as much. We can really just rely on our calculator here. I'm going to plug in or just multiply out in my head. So first thing I have is 2 times 4 is going to give me 8 dx dt. Then I have negative 3 times 11, which is going to be negative 33 dx dt. Then I'm going to do negative 3 times 4 times 0.1. So negative 3 times 4 is negative 12 times 0.1 is going to make it negative 1.2. And 2 times 11 is 22 times 0.1 is going to make that 2.2 equals 0. Now we can combine some like terms. So for my dxdt, I have 8 dxdt and a minus 33 dxdt, so I'm going to get negative 25 dxdt when I do 8 minus 33. For the numbers, I have negative 1.2 plus 2.2, so 2.2 minus 1.2 is going to give me a 1 here, equals 0. And I just want to solve this like a linear equation. So I want to just isolate the dxdt the way we would if we had negative 25x plus 1. We would subtract 1, divide by negative 25 to get the x by itself. We're going to do the same thing, but we're isolating dxdt instead of a regular x like we would with the linear equation. So I'm going to start by subtracting 1 from both sides. That way I get negative 25 dx dt equals negative 1. And then I can divide by that negative 25. And I could plug into my calculator to see what this is. I get 0.04. What does that even mean? Well, I'm going to look back at this setup that I highly recommend. It helps you get the full credit answers. It's 0.04 drives, which is really in 1,000. So this is 1,000 drives per week. So we're going to multiply this by 1,000 and do our interpretation. 0.04 times 1,000 is 40 drives per week. So to interpret this, we're going to say the derivative we were given and how it affected the derivative we found. So the derivative we were given is that they want to increase their price. So we're going to say as the price increases by 10 cents per week, this one was supply, not demand, right? It's called the supply equation up here. The supply is doing what? Is it increasing or decreasing if we got a positive 40 as our answer? It's increasing. The supply is increasing by 40 drives per week. I think it makes a lot more sense to multiply out by that 1,000. That way it actually makes sense. 0.04 of 1,000 doesn't mean too much for me, but 40 flash drives makes more sense. So as the price increases by 10 cents per week, the supply is increasing by 40 drives per week. That means they have 40 more flash drives sitting on the shelves than usual. That little price increase does impact how many flash drives that they have sitting in stock.